We evaluate on the held out set every so often during training, watching both eval loss and eval accuracy. Your reference points are simple. An accuracy of 1/2 and a loss of log 2 mean the model is guessing. Anything meaningfully above that means it is genuinely learning preferences. Watching the curves, training loss falls below log 2 and accuracy climbs off 50% into the mid-60s or low 70s, which is typical at this scale. For reference, Instruct GPT's 6 billion parameter reward model hit around 72% on similar data, so a small model in the 60s is doing real work. Here is the framing that matters most. Reward model quality is the single biggest bottleneck in RLHF. If held-out accuracy is stuck below about 65%, downstream reinforcement learning will likely not improve the policy in any meaningful way. Accuracy is one number, but it hides the shape of what the model learned, so we look deeper. We collect the reward for every chosen and every rejected response and plot their distributions. A healthy model shows the chosen pile sitting to the right of the rejected pile, with a positive average gap between them. You also plot the gap directly, with a line at 0 as the decision boundary. Anything left of that line is a pair the model got wrong. Seeing the overlap, not just the accuracy, tells you how confident and how separated the model really is. Now the failure modes, and the first one is sneaky length bias. Reward models love to give higher scores to longer responses, regardless of whether the extra words add anything. So we plot reward against response length, fit a trend line, and check the correlation between the two, and if that correlation is strong, the model has partly learned reward equals verbose. You probe it directly, a short correct answer versus a long rambling one, and see which the model prefers. If it picks the windbag, you have a problem. The second failure mode is sycophancy. The reward model learns to reward responses that simply agree with whatever opinion the user stated, even when the user is plainly wrong. The classic probe: the user insists the earth is flat. An honest response politely corrects them. A sycophantic one says, "What an interesting perspective. Your view is valid." If the model scores the flattering agreement above the honest correction, it has learned to be a people pleaser instead of a truth teller. You fix this with adversarial data, where the sycophantic answer is explicitly marked as the rejected one. The third and most important failure mode is reward hacking. Once you let a policy optimize hard against a learned reward model, it will find the model's blind spots and exploit them, racking up a high predicted score while producing genuinely low-quality output. This is Goodhart's law in machine learning. When a measure becomes a target, it stops being a good measure. The reward model is only an approximation of true human preference, so optimizing it too aggressively eventually optimizes the gap between the two, not the thing you actually care about. A few more failure modes round out the picture. Format bias: the model prefers bullet points or markdown regardless of content, fixed with diverse formatting in the data. Distribution shift: the policy drifts to outputs unlike anything in the reward model's training set, where its scores become unreliable, which is a core driver of reward hacking. And annotation artifacts, where the model latches onto superficial quirks of how annotators wrote or picked responses. The common thread: a reward model only knows the distribution it was trained on, and it gets fragile the moment you leave it. Now the deeper why questions, the ones interviews live on. Why pairwise rather than pointwise regression onto a numeric rating? Because absolute ratings are noisy and miscalibrated across annotators. They demand everyone agree on what a 4 means, and they are harder and slower to collect. Pairwise comparisons sidestep all of that. They are more reliable. They automatically cancel out each rater's personal scale, and Bradley Terry gives you a proper scoring rule on top. The comparison framing is not a minor convenience. It is why the whole approach holds together. If reward hacking is the disease, what is the cure during reinforcement learning? You put the policy on a leash. You subtract beta times the KL divergence between the new policy and the original reference model from the reward. In plain words, the policy is free to improve, but it pays a price for drifting too far from how it started. That keeps it inside the region where the reward model's scores are still trustworthy. This is the bridge into the PPO notebook, but it is born right here, from the reward model's limits. There is beautiful empirical work on exactly how reward models fail under pressure. Gao and colleagues, 2023. Measure distance from the reference as the square root of the KL divergence. At small distance the true reward rises, the model is a good proxy. Push further and the true reward peaks, then falls, as the policy starts hacking. And notably, best-of-n sampling and reinforcement learning follow different functional forms, so there is no single universal law, just be careful which one you quote. Larger reward models shift the whole curve rightward. They tolerate more optimization before they break. A very common interview prompt, reward model versus using a large language model as the judge. The trade is cost against flexibility. A trained reward model is a single forward pass, roughly 100 times cheaper per evaluation, which is the only thing that scales to the millions of judgments reinforcement learning needs. An Llm-As-Judge is more flexible. You can change what it grades with a prompt instead of retraining, but it is slow and expensive. The elegant middle ground, use the expensive judge to label data cheaply. Train a fast reward model on those labels. That is essentially Rlaif. That idea generalizes into a real trend worth naming. Modern reward models often blend human preferences with AI-generated ones, reinforcement learning from AI feedback. Anthropic's constitutional AI is the landmark example, where AI feedback partly replaces human annotation. Newer approaches like iterative DPO and self-play methods have the model generate its own preference data, cutting annotation cost while holding alignment quality. The through line, use a stronger model to grade a weaker one, showing you understand that human to AI feedback spectrum signals you are current with the field. If an interviewer asks what makes a good reward model, do not stop at accuracy. A strong answer lists several properties. Accuracy, yes, it predicts held-out preferences, and remember the ceiling is only about 75 to 80% because humans themselves disagree that often. But also calibration, scores tracking real quality gaps and not just ranking robustness, not being gamed by length or style, generalization to prompts unlike the training set, and consistency, similar inputs getting similar scores. A model great for ranking is not automatically great for optimization, which needs smoothness without exploitable spikes. Let us anchor the production reality, because the numbers come up. Frontier reward models are often tens of billions of parameters, trained on 500,000 to a couple million preference pairs, which at several dollars a comparison can mean millions in data cost alone. Teams of dozens to hundreds of trained annotators work from detailed rubrics, with calibration tests and inter-annotator agreement tracked, Cohen's kappa above about 0.7 as a quality bar. And the single biggest determinant of reward model quality is not the architecture, it is the annotation pipeline. Bad labels bake noise straight into the judge. In production, you never set the reward model and forget it. You continuously compare its scores against fresh human evaluations, and when they start to diverge, the model is going stale or being gamed. You watch the score distribution drifting upward across the board, a tell that the policy is exploiting weaknesses. You break accuracy down by category, because coding, math, and creative writing can differ wildly. And you retrain on new preferences gathered from the latest policy, which closes the distribution gap but creates a moving target, the reward model and policy chasing each other. Let me name how this gets tested, since reward modeling is core at Anthropic and OpenAI. Expect a 30 to 45-minute design prompt. Build a reward model pipeline from scratch, where they want data collection, annotation quality, architecture, training, and evaluation, not just the loss. Expect a 5-minute ask to write the Bradley-Terry loss from memory, and expect a discussion of reward hacking with concrete examples and mitigations. The red flag they watch for: a candidate who can only recite the loss and never mentions data quality, calibration, or how the thing fails. So here is what you can now do. You can explain why RLHF prefers pairwise comparisons over raw ratings, derive the Bradley-Terry model and write its loss as plain cross-entropy, and describe the backbone plus scalar head architecture and why the language model head gets removed. You can diagnose length bias, sycophancy, and reward hacking, and tie them to Goodhart's law and the Kl Leash. That is the judge at the center of RLHF, and it is exactly what the interview wants to hear. Follow along on the frontier path, where Moot studies the machine learning interview in the open.